Hello, Josh Sideris here. In this video, I'm going to discuss how you would go about designing and building an H-bridge. This is part two in a two-part video series on H-bridges. The first part was how not to build an H-bridge, where I talked about the hazards in building an H-bridge, even when you're sourcing your circuit from a reputable source, like a textbook or a reputable website. So if you haven't checked out that video, check it out now before you watch this one. And there'll be an annotation and a link in the video description. Today, one of the things that we're going to be doing is designing an H-bridge, obviously, but I want to focus more on the design thinking itself. How do you go about approaching the problem of designing an H-bridge from scratch? What are the things you need to consider, and what do you need to think about when you're approaching the problem? Now, it would be somewhat counterproductive for me to sit here and give you a schematic that you can just follow to build an H-bridge. There are just too many variations, and really, just like any engineering project, you need to go back to the requirements and you need to think about what your needs are for this project. What is the cost of the project? How much load do you need your motor to lift? Do you even really need bidirectional abilities? Do you need circuit protection? And things like that, right? So that's why I built that's why the first video in the series was how not to build an H-bridge. The point I was making with this video is that you can't just copy some schematic online and hope that it will work for your requirements. You need to understand your requirements intimately, and then you need to decide what features you want to add to your H-bridge design from there. And this isn't just for H-bridges. This is for any type of electronics or any type of engineering project. You start from the requirements and then you decide what features you want from there. Once you've analyzed and understand the requirements of your project, you need to decide on what motor you want. Choose one that has the necessary amount of torque and speed that fit your requirements, but also consider other factors like size, weight, power consumption, and cost, as well as any other features that you need in a motor. Once you have all your requirements in check and you've selected a motor, now it's time to build your motor controller. It's important that you start the motor controller after you've selected an actual motor because, well, things change based on the motor, right? I mean, consider this. If you were building a 5 volts motor controller, something like for a little modular robot with those little 5-volt motors, right? You could power that using like a 4-transistor H-bridge. Very simple, and you could plug that into something like an Arduino or whatever. But if you have like a huge robot motor, like this, high power motor, you can't just power this with BJT transistors. This is heavy duty. You need power MOSFETs for this, and it's going to be a complex circuit, and your power MOSFETs have a chance of exploding, which is exactly what happened to me when I was setting this up with a friend. And then another thing you need to consider is circuit protection. How are you going to ensure that things don't break when you're running your H-bridge? There's a lot of hazards that could happen, like back current, or the worst would be back current going into the CPU and destroying your microcontroller or your other electronics. Or you could get stuff like, well, worst case scenario would be something gets shorted out. Your power supply, if you're running your motor off of batteries, you don't want to short out your batteries especially. So there's a lot of hazards. You can build circuit protection to protect your components. And I'll get back to that in just a minute. But before we do that, let's actually design an H-bridge. It'll be a good exercise, and we'll go over the design for an H-bridge that I like to use for low-power robot projects, and then I'll talk about circuit protection and upgrading it with other electronics and some of the other design considerations. Here you have PNPs on top and NPNs on bottom. Of course, activating this is easy. You just need to activate one of the top PNPs and the opposite facing NPN counterpart. Why not just use all NPNs? Let's say that we did put NPNs on the top like this. With this design, the electricity that activates the top transistors also has to travel through the motor. There is a bit of extra resistance here, which could potentially impede the top set of transistors, depending on the state of the motor. But there's actually a much more serious problem with this design. Let's say you had a 12-volt VCC and you were trying to activate the transistors with a 5-volt input signal. Well, that 5 volt is going to be pushing up against the 12 volt that's going to be applied to the motor, so the transistors in this state won't even fully turn on. I'd also recommend not using PNPs on the bottom because the variable impedance of the motor will inevitably affect their activation state, but also because PNPs don't work optimally when the collector is grounded out. Consider this for reference. In this circuit we have a load resistor, highlighted blue, before a PNP. Note that there is a 4.3 volt drop over the load. The reason we're losing 0.7 volts is because the transistor here cannot turn on all the way. If it hypothetically did turn on all the way, the base pin would be getting shorted out, which in turn would cause the transistor to slow down again until it reaches an equilibrium state. Now let's see what happens when we put the load after the transistor. It's the same circuit overall, but now we have almost the entire 5 volts being dropped over the load. This second configuration is the correct way to use PNPs. As a rule, when working with binary junction transistors, you can put your load after a PNP or before an NPN. Now we need to think about how to activate these transistors. Given the voltage and impedance in these diagrams, we know that the current going through the motor during nominal usage will be 12 volts over 100 ohms, which is equal to 120 milliamps. Okay, but this thing isn't always going to be running nominally. When your electric motor is lifting a heavy load, it uses more power. This might make sense intuitively, but how does it really work? Remember, a motor is just a large spinning coil. It has an internal alternating current, and it has an impedance as a coil that spins. And what happens is when you hold onto the shaft or it's lifting a really heavy load, the motor spins slower. And what that does is it lowers the impedance of the motor, resulting in a higher current. Power is equal to current times voltage. So if you have the same voltage over the terminals of the motor, but more current, you're going to have more power being dropped over the motor. That being said, we don't necessarily want to accommodate stall currents. A stall current is what you get when the motor absolutely can't spin, and so it really is just an inductor, a large inductor. And of course, if you leave a positive voltage on an inductor, it behaves very similar to a wire. So that's your stall current, and it would essentially be something like a short circuit. So when we design the H-bridge, we want to make sure that we can accommodate a maximum stall current. Let's say we want to allow up to 1 amp to pass through the motor. Just like I discussed in my transistor tutorial video, the current that is allowed to pass through BJT transistors is typically around 100 times greater than the current that enters or exits the base. So to allow 1 amp to pass through the transistors, you'll need to sink at least 10 milliamps on the PNPs and source 10 milliamps on the NPNs. That's not too bad, and you might be able to control the transistors directly from some microcontrollers through a resistor, of course. But for completeness, I'm going to take it a step further and include a Darlington pair configuration. Once again, this is a trick I discussed in my transistor tutorial video. It's using this configuration that you can get a maximum current amplification effect of 10,000 instead of just 100. That means you can control a relatively powerful motor using a low power, low voltage microcontroller. Here's the final result after adding the Darlington pairs and supporting electronic components and connecting them to a microcontroller represented here by a clock signal and an array of switches. These obviously are the Darlington pairs themselves. Note that I used NPNs on both the top of the circuit and the bottom. That's really a preference of mine, and you could always go with PNPs instead of NPNs. I just find this circuit a little bit easier. One of the added benefits to using both PNPs on the top and the bottom of the circuit is that from the microcontroller's perspective, a high voltage always means that that side of the transistor is going to be on. So there's no more confusion with a low voltage actually meaning on for PNPs. Now a high voltage is always on. So if you have a high voltage, it'll activate that part of the circuit. And of course, we're following the same rules with how we position our transistors as before. On top, we're using NPN Darlingtons to ground out the PNPs through a resistor, and then on the bottom Darlingtons, we're using NPNs to actually source NPN, the main NPN transistors on the H bridge. Now consider these resistors. These are feeding directly into the main transistors on the H bridge. The values are somewhat arbitrary, but as a rule, you want to have them low enough that the transistors on the main H bridge function as a switch, so they're always on, so you're not limited by current, so the maximum amount of current will always be able to pass through the motor. But if you wanted to, you could actually increase these a little bit, and then you could have protection, or at least a little bit of protection against stall conditions. Like imagine if you had a stall condition and your motor resistance went to 0, or I should say impedance. You can actually limit the motor, the current going through the motor using these transistors by having a larger resistance here. So I'll leave that up to you. The downside of doing that though is that in a stall condition you won't get as much power. So if you actually were trying to lift a really heavy load, you won't get as much power out of that. But the benefit is that the batteries or whatever power source you're using won't get shorted out. And I've built robots before where every time it crashed into a wall, the CPU would restart, and it was a wireless robot, and that would disrupt the wireless link. So limiting the current using using the transistors is certainly a feasible strategy, but it's something that you need to design and you need to think about. And here I have the resistors that are driving the outside Darlington pair transistors that are responsible for driving the inner transistors. Now I didn't give too much thought to these resistances, and this is going to change from circuit to circuit. As a rule, you want to make sure that the current entering the bases of the Darlington transistors activate them enough to fully activate the inner transistors. And that's really going to depend on the inner resistances that you're choosing for the inner resistors, as well as the voltage of the microcontroller. You also want to make sure that the current that's leaving the microcontroller is within the microcontroller's specifications. If you draw too much power from a microcontroller, you could risk damaging the transistors and the delicate electronics in the CPU, in the microcontroller. So that's how you choose these. I didn't give it much thought, and I'm sure that these are really stupid values. I'm going to post a link to this circuit though in the video description, and you can go tweak the values in a simulator and play around with it and choose values that are right for you. The goal that you should have in mind is when the motor is on, you want all the voltage of VCC to be dropped over the motor, or at least as much as possible. So and of course, there's other requirements with, don't short out your microcontroller and don't draw too much current and stuff like that. So choose values that work for you. And but the Darlington pair setup here should work with a wide range of microcontrollers, even low power controllers, and for a wide range of low power motors. All right, now here it is in action, right? So you can see that when the clock is on, we have 12 volts being dropped over the load here. And of course I could just flick these in a different pattern here. Oh. And there you go. So current is actually flowing the opposite direction through the load. And you can see that current, a little tiny bit of current is going into each side of the H bridge here. In fact, I'm going to increase the current speed so you can see that. In this simulation, with this design, the amount of current passing through each Darlington transistor on the outside here is less than 5 milliamps, so it's very little, and it's driving this motor at full speed. There's a few conditions that we want to avoid when we're building our H bridge, but we've got to be careful there are forbidden conditions that could occur. So if we activate this side of the H bridge and this side of the H bridge, then current will actually short out through these two transistors. We can run that, and it actually broke the simulator because maximum current exceeded. Now there's no built-in short circuit protection in this H-bridge design, and if you wanted to, you could always go with a Schmitt trigger, or you could perhaps limit the values of the inner resistances, as I mentioned before. There are different ways of handling that. Perhaps the best way to handle it, or the simplest way, is just to make sure that condition never happens in your microcontroller code. But that can be tricky, and mistakes happen, and you don't want to fry your electronics. So if you have the extra time and the extra budget, I would recommend upgrading this circuit with a little bit more circuit protection than just relying on code. In fact, I've written code before that guarantees that one side of the H bridge will not turn on at the same time, both transistors on one side, and somehow it still happened. Perhaps because the microcontroller was low on power, and it got into a weird state, and somehow one whole half of the H bridge activated at once, and I burned my fingers on one of the transistors. So you got to be careful. All right, there's a few more things I want to discuss in this video regarding circuit protection, right? You might have seen diagrams of H bridges that look like this with really complex circuitry and stuff, right? So let me just explain what some of this stuff does. All right, we have two components that I didn't talk about before in this diagram. We have diodes over all of the transistors, and we also have a capacitor, and that's pretty common for these types of circuits. In case you're wondering what these all do, I'll start with the capacitors. Capacitors have the effect of smoothing out current. So if you have a circuit that has like a motor or some other electric device where you're going to get current spikes, and when I say spikes, I mean like sometimes your motor will be running smoothly and then it'll crash into a wall, then all of a sudden you get a huge spike in the amount of current. You got a stall condition or something. Those spikes are kind of dangerous for your electronics. Like if you have a microcontroller and you're getting voltage spikes, your microcontroller might shut off, whatever. So having a capacitor attached to your VCC line is probably a good idea whenever you have a motor involved. And really, it has less to do with H bridges, and it has more to do with just having an unpredictable source of current spikes. And so it's a good idea to have. And I'm not going to go into this video in how to choose a capacitor. That's a whole other topic. But I mean, really, it's any capacitor. The bigger the capacitor, the better. You know, if you can afford a high rated a capacitor that has a lot of capacitance, that's great. If not, then go for something smaller. But as long as it can handle the voltage of VCC plus a little bit extra in case there is a back current from the motor. And now, what about these diodes? These crazy diodes that stretch across each transistor. Well, these are called flyback diodes, and even though the types of transistors I'm showing in this diagram are not BJTs, these will still work with a BJT based H bridge, and it's probably a good idea to include them, right? Because what these diodes do is, well, your motor is this giant coil that has a lot of energy built up into it, right? And what happens is if suddenly you switch from going forward to reverse, you still have all that voltage built up in your motor. You have a lot of potential energy. So what these diodes do is they allow that energy to drain out. And if you don't include the diodes, that energy has to go somewhere. And if you had like a crazy voltage spike as a result of a stall current or a stall condition or something like that, then what you could have is current going backwards through the transistors, and that's a very dangerous condition to have because you could damage your transistors, you could short them out. So this is a form of circuit protection. It's very good even for low power motors, low power circuits. It doesn't hurt to include a few diodes just in case. And I can demonstrate this actually with the circuit simulator to see how useful these are. But we have to change the motor from a resistor to a more realistic representation. We're going to switch it to an inductor. So here's our friendly circuit again, and all I've done is I've changed the resistor motor thing to a resistor plus an inductor, and that's actually a more reasonable representation of a motor in my opinion, right? And then I've added these 4 diodes, these flyback diodes. I didn't include the I didn't include the capacitor because the simulator was behaving a little weirdly when I included it. So let's see what happens when I turn this H-bridge on. Oh, it's a little laggy here. So take a look what happens when I include these components, okay? So we're gonna have to slow this down, I think, a little bit to fully appreciate this, and even the current as well. Okay, so when the H-bridge turns on, current builds up through here, and then it continues to flow through even after the current shuts off. And of course, this is a very common situation when we're running when we're using an H-bridge. We use PWM signals to turn the motor on and off very quickly. Well, the motor can't actually turn off because it's this giant coil, so it has this inductance. So this is what realistically would happen here, is that you have this voltage that gets built up inside the motor, and where is that voltage going to go? Well, it's being forced out by this coil, so the current pushes through, and luckily we've added a path for the current to take. Now, the reason I didn't include the inductor in the last simulation, the video that I made just a minute ago, is because if I remove the inductor, if I include the inductor, if I had included it, but I removed the flyback diodes, then it actually breaks the simulator, because what happens is you have current that's flying out of this motor, and it has nowhere to go except for to like break one of the components here. So the simulator won't allow that, and it actually shuts down the simulation. So if I include the inductor, which is, this is a real motor, I have to include the diodes in the simulation, otherwise stuff breaks. In fact, here's an even better view of it. I've replaced the clock with a high voltage signal, so now this motor is spinning at full speed, and as soon as I turn off the bottom H-bridge half, right, watch what happens. Take a look at what happens to the current passing through the motor that normally would be going through this transistor, right? It has to find a path out, and this flyback diode allows it to find a path out. So that's pretty much it for this video. I think that I've gone on long enough talking about how to build an H-bridge, and look, there's a lot more to it than that. This is just the tip of the iceberg. Imagine if you were sending a rover to Mars. You can't just go and fix stuff that breaks, and it's a very expensive mission and stuff. So if you're doing something like that, it would be prudent to take even more precautions when it comes to isolating your motor electronics away from your computer. And I've seen setups where they actually use like optical sensors to instead of transistors, using optical transistors that only activate when light is shone on them, and that allows complete isolation from your computer electronics from your motor electronics. And there's all kinds of things that you can do with things like that. But again, this is supposed to be an introduction, and I don't want to dwell too much on that. The principles that you learned here also apply to MOSFET H-bridges. You need to design the H-bridge a little different if you're going to go with MOSFETs. So you can potentially use this stuff for more powerful circuits and stuff. But again, what I really want to emphasize is the design thinking. Go based on your requirements. You know, it's actually a linear process. You start with your requirements, you decide on a motor, and then you end up with the rest of the electronics kind of fall in place. And then there's a little bit of cyclic ideation where if you come up with a design that's too expensive, then you need to go back and revise your requirements. But yeah, that's the takeaway message here is when you're designing your edge bridge, start with the requirements and everything else will fall in place. It's pretty simple stuff. So if you have any questions, you can private message me or leave a comment in the down below. Be sure to like the video and subscribe for more. Josh Sideris.